All right. Hello, this is Alex Aljets. This is my update for February 11th. I'm working on using BINDSMART to evaluate protein-ligand interactions right now with CA2. Um, so first, I'll talk about HOLIGNN, um, which we use to classify ligands of OATPs as substrates or inhibitors for it. It performs pretty well. As the figure shows, it performs generally better than just the ligand-based classifiers. Um, but we would like to compare how it does to other proteins, and specifically proteins that are easier to work with, like carbonic anhydrase 2, which is smaller than OATPs. It doesn't have significant conformational changes. It has a lot of crystal structure data, um, stuff like that. It's generally pretty easy to work with as far as proteins go for these substrate inhibitor stuff. And then before I get into how I'm working with, the neural network, I'll go in, like we start with a ligand and like some kind of structure, whether it's from AlphaFold or some kind of crystal structure. And then from that, we can dock them with, something like Rosetta, and then put that docking ensemble into PLIP, and then convert it into PLIF, which is basically just what we feed into the neural network to train it on, kind of recognizing substrates and inhibitors and stuff. So it's special because we're looking at the ensemble rather than just the ligand, of course. CA2, again, seems to be mostly pretty typical as a subject. There doesn't really appear to be significant conformational changes. Even this, his one is just like I couldn't see it on Pymol when I was, you know, looking at it in there. His conformational change. It does use a zinc ion, which isn't accounted for when, we're doing docking and plugging into PLIP, which could be cause for concern, but it seems pretty insignificant as of now, I believe. So basically, CA2, higher quality source of data, more complete um, in terms of the structure, more ligand data for substrate inhibitors, that kind of thing. Basically, the CA2 data is high quality, and the OATP data is the perhaps questionable McDonald's chicken nuggets. A more quantitative way to say that is with the PLDDT reports from AlphaFold, which is basically just how confident AlphaFold is in the position or its projection of the structure with OATP 1B1, which was one of the more better performing OATPs. It's pretty often not confident at all. And with CA2, it's pretty much always, like in the high 90s for its confidence. Um, so it's a lot more comfortable with CA2. So basically how we're gonna evaluate bind-smart effectiveness, or how we did evaluate bind-smart effectiveness, we could do with the ligand-bonded crystal structures, docked apocrystal structures, which would then be docked to ligands. Um, and then with AlphaFold 2 generated structures, um, we, I think, kind of more focused on, at least I focused on in my workflows, docking the apocrystal structures, specifically 7QGZ, which is just a PDB code for CA2. Um, so I guess kind of oddly, most of my work This past semester and a bit has been pretty much on this slide with docking and plip stuff. Um, so we used the APO crystal structure, docked it against 460 ligands, or I suppose Theo docked it against 300 and I docked it against about 150. And then after that, I inputted those docking results to plip, um, and then reformatted plip to plif. It took a while because of some issues that I ran into, which were, more or less just kind of more storage based and not like a bigger picture issue. So some of the issues, the docking and flip process, it generates like a million files. Because if we're doing 400 um, ligands and doing 1,000 poses, which is how many poses we do per ligand. It's hundreds of thousands of files that we're making or that I'm making. Um, so I kind of had to deal with this more or less on the fly with, zipping and unzipping stuff and using the command line. So definitely some learning moments there, some experience gained on that kind of stuff. And then the flip storage issues, you can pretty much zip or rezip the stuff that we were opening or the stuff that I was opening with just like a line of code on the job that I'm submitting. And then another problem was that Plip just didn't work for 11 ligands. Originally, it was about 150. And then with resubmitting and resubmitting, it got down to like a list of 11 stubborn ligands that just Plip wouldn't read for whatever reason. Generally though, they were like the numbers, like I think like 667 was one of them. This one says 067, like 9E4, 9E9. So I'm assuming it's just some kind of odd way that Plip's looking at numbers there, as opposed to something like, VYV, that kind of thing. So I say relatively smooth, worked through docking, plif stuff. Um, so now all that work that I did, all the fights that I had with the computer can help us learn about BINDSMART and get us actual data and kind of flex how good it is. It's all right. It's pretty good. Um, so this is using regression data with the CA2s to predict KI values. Um, so with the table, which total, this is pretty much all Joelle's work. So shout out Joelle, or as far as I know, pretty much a lot of Joelle's work. So I definitely don't want to take credit for this, but I'd like to present on it. I think it's pretty cool. So with the crystal structures that were already bonded to ligands, the R squared value for the regressions like 74. And then with um, the docking APO structures, or with that 7QGZ, the model actually performs better at like 78% R squared. And both of those pretty significantly outperformed the purely ligand-based like regression methods. And the best one was the ECFP, which had like 64% R squared, as you can see. So I thought it was pretty interesting how the docked um, structures, like the simulated docking structures, were like outperformed the crystal structures just because it's simulated and not like like in my mind, usually the gold standard is kind of like a good crystal structure. Um, but talked to Joelle. They said it was probably due to the ensemble, like the, 10 or 100 or however many poses the the neural network got to look at and be trained on, which I thought was pretty interesting. I thought that was kind of interesting how the simulated one would outperform the real one. And then this is another, I guess, just kind of interesting graph, I thought, um, which is talking about the different, how the crystal structures compare to the docked simulated poses in terms of which residues, which amino acids are interacting, um, with the ligand, kind of in different poses and stuff. So two interesting things or areas where noise was added was with CA2 residues falsely interacting with the ligand, which you can kind of see in the crystal structures, kind of the real structures. There's a big blank spot in this part of the graph. Um, but then in the the best pose, 10 best poses, 100 best poses, there's a lot of, I guess, reported interaction in those spaces, which would probably just be noise and something that's unwanted. Um, and then in terms the blue marks that I marked, I guess, it's ignoring residues that are known to interact with ligands on CA2 in a docking thing. Um, so up here in the crystal structures, there's definitely some like action around the known residue parts up here. But then with the simulated docked poses, there's more of a low percentage on that top half, which I thought was kind of interesting, especially in the face of the docking outperforming the crystal structures, even with all that noise. So I guess that kind of tells me that as our docking tools get better and better and have less and less noise, the docking is just, or the docking, um, I guess classifying or regression performance is just going to get like way better as less, kind of junk is introduced in there. So to revisit the three different kinds of structures again, obviously the crystal structures, 74% R squared, the apo structure, 78% R squared. And then the AlphaFold 2 generated structures, I was able to generate just a normal AlphaFold structure for CA2, and then one without reliance on crystal structures, um, because we kind of wanted to simulate how we were doing with OATP, how we were testing with OATP, which had a ton less crystal structures to reference than CA2. But these, like the PLDDT stuff, it was basically the same. It was pretty similar, so I decided not to compare those, and they weren't tested in regression task, and also they might have been a little irrelevant because of AlphaFold 3. So, which kind of leads me to future steps, which I think would be for me working on how to integrate AlphaFold 3 into kind of that docking plif workflow, replacing the docking part, obviously, because AlphaFold 3 has the docking feature, I guess. And then, including that, I guess, as we move forward. And then, um, using other proteins with BINDSMART, kind of further vetting its performance, seeing the kind of performance trends like, oh yeah, when there's a bunch of crystal structure data or, accurate KI data or whatever, how does BINDSMART react to that? Um, with other proteins, that's definitely on the list. And then one kind of thing that I was wondering about, I guess, was that the performance of um, the docking outperforming the crystals was probably due to an ensemble of poses that the neural network got to look at. But with AlphaFold 3, it's probably only going to have like 1 to 5, or at least that's the volume that I've generated with AlphaFold 2 is like 1 to 5 poses. And I'm kind of interested to see how that would impact like any regression results or classification results, stuff like that as we keep going. So that's kind of what I have going on right now, or and had going on in the past semester. So thank you to everyone who has helped me fight my battles with storage and everything like that. Thank you. I hope this wasn't too long or rambly. Definitely tough to judge without a live audience. So thank you.